I'm Aliff Amierul bin Rusli, ID 25438. My title is Seismic Redatuming Imaging. So now we are going to look at what the problem that Seismic Redatuming Imaging wants to solve. So in the diagram, we can see the lithology is divided into A and B. Okay. Now we can see an anomaly in the near surface lithology, which is colored in blue. It has a very low velocity of around 1000 milliseconds. And the surrounding lithology is around 1500 milliseconds. So when we wanted to map out the reflection on the B part of the lithology, what happens in the area of XB is that the amplitude will be lowered due to multiples or in the area colored dark blue, and also the travel time in the lithology part B will have a slower two-way travel time. So what happens is, because there is a strong heterogeneity, it causes strong scattering effect, it causes dispersion, it causes internal multiples, mode conversion, and also inelastic losses. So how this will affect our seismic image is, it causes the seismic image to have amplitude and frequency loss. It causes us to interpret false structure, and it also shows poor event continuity. So the way seismic redatuming imaging works is by moving the source and receiver location from the surface or the old datum to a new virtual depth. This is called the redatuming. And after that, we are going to use that new redatum level for seismic acquisition. This method wasn't new because it was first proposed by Barry Hill in 1979 as static correction. But nowadays, people have found other use for it, especially in solving complex overburdened subsurface imaging. In this top figure, we can see the effect of shallow gas cloud on the amplitude of the reflector. After full waveform redatuming, we can see that the reflector below the gas cloud are much more clearer or have a higher amplitude, so we can see the primary reflections more clearly. At the bottom figure, we can see the effect of gas cloud. It shows here, before redatuming, the two-way time travel shows a very low velocity, but after redatuming, the velocity of the reflection below the gas cloud has been corrected, and it shows a much higher velocity than before redatuming. There are many advantages of using seismic redatuming imaging. One is enhanced primary reflection data. The second one is increased signal to noise ratio, and three is preserves amplitude better. The last one is, even using heavily smooth velocity model, the time kinematics of many major reflection events on short girders after redatuming are consistent, and it is not necessary to obtain high resolution overburden velocity model as a starting model for redatuming. What this means is, even if we do not have a detailed overburden velocity model, using a simple one, a simple model-based velocity, it is enough to obtain a high resolution for overburden velocity model as starting model for redatuming. We can see on the left figure, the effect of redatuming is very clear. After redatuming, The primary reflection data has a higher amplitude, and the primary reflection data is more clear for interpretation. We can see the figure on the right, where redatum image is on the top and the migrated image is below. We can see better event continuity on redatum image, so it is easier for geophysicists to interpret subsurface structure after we have applied seismic redatuming imaging. However, there is still some limitations on using seismic redatuming imaging. One of them is model-based redatuming is influenced by limited recording aperture or irregular source and receiver distribution. And it also requires correct velocity errors above the datum to some extent. What this means is this effects as a blurring filter and thus introduce artifacts and reduce the resolution on our seismic redatum image. The standard velocity model-based redatuming using velocity is it only takes into account for Born approximation. What Born approximation means is assumes that waves have only scattered from heterogeneities in the medium one, thus requiring the data contains only of primaries or singly scattered waves. This proves to be disadvantageous because we require significant prior information about subsurface reflectors or reflections prior to multiple prediction and removal before we can do seismic redatuming imaging. In order to overcome some of the previous limitations, some research by Zhu et al. Proposes using the least square redatuming method. So how does it work is subsurface medium are divided into overburden and underlying part. And model space consists of two components, the overburden reflectivity and the virtual data on the datum. So by splitting the entire subsurface medium into overburden and underlying parts, it could regard the redatuming as two-parameter inverse problem. And this means that the overburden reflectivity and the virtual data are estimated in sequence or simultaneously. So what this method has achieved is it managed to reconstruct the reflection seismogram, which would be stimulated and recorded by the virtual sources and receivers on a given datum plane. So what least square redatuming has been able to achieve is it effectively suppresses artifacts due to incomplete or irregular observation. It enhances continuity of reflection events from deep structures. It mitigates the effects of overburden velocity perturbation and the source wavelet. It shows higher resolution than model-based redatuming, and also better velocity estimation and seismic imaging for deep targeted reservoirs. On the left figure, we can see the differences between virtual short gathers using model-based redatuming and also LSR method. We can see that the LSR method on the right shows better amplitude and shows a better primary reflection data. And on the right, we can see the figure shows reconstructed short gathers for a virtual source using model-based redatuming and also LSR method. The LSR method on the right shows better reflection data and also a higher amplitude. Another method brought forth by Aliff to challenge the usage of model-based redatuming is using Marchenko redatuming and convolutional interferometry method. So in this method, without needing to put either sources or receivers in subsurface, it uses estimates from Green's function from virtual sources in the subsurface using just data measured at the Earth's surface. How do they do this? Is by creating special wave fields also known as focusing functions that may focus energy at a specific subsurface location. So these synthesized primaries were used to produce images free of multiple related artifacts via linear RTM. Although this method seems great, there are several requirements that make it hard to apply on real-world scenarios, such as knowledge and accurate deconvolution of the source wavelet and co-location of sources and receivers. We can see from the image below that Marchenko Redatuming on the left produces only the first arriving event but not the scattered multiples. This is good for seismic interpretation as the image does not create any fault structure in the subsurface. In the future, the problem of model-based redatuming will be solved by using various of least squares inversion methods, Marchenko redatuming, or radon redatuming. However, the criteria for any method that are going to be used will be decided by using exploration budget and whether which process are more computationally efficient. Because model-based redatuming still needs a lot of information above the new datum point, most of the time modified version of Marchenko redatuming is currently popular in application. So Xiao in 2018 have studied vertical seismic profile and change it into surface seismic profile by using radon domain interferometric redatuming. He concluded that this method suppresses truncation of artifacts and accuracy and temporal resolution has also improved with this method.